Every day, vast amounts of information are generated across every sector, from financial markets to healthcare, from e-commerce platforms to scientific research. This constant influx of data holds immense potential, but only if we possess the tools to understand it. The challenge isn't about collecting data, it is making sense of the sheer volume and complexity. Imagine a business that records every single sale, every customer interaction, every product detail. Without a structured way to access and analyze this, it remains just raw numbers. How do you identify your most profitable products? How do you understand customer buying patterns over time? Or even how do you optimize inventory based on demand trends? It is indispensable language for interacting with relational databases which are designed to store, organize this critical information. SQL provides the practice command needs to extract, manipulate, and analyze the data, transferring it from a chaotic collection into the actionable intelligence. This session is designed to equip you with these fundamental SQL skills. We will build from the ground up, exploring core concepts and progressing to advanced techniques. Expect a clear, practical approach with hands-on coding example that you can follow along with. Let's begin our deep dive into the SQL for data analysis. Our primary objective today is to empower you with the essential SQL skills required to effectively navigate, analyze, and transform vast datasets. Whether you're aiming to extract specific pieces of information, identify hidden trends, or even make data-driven decisions, the techniques we'll cover will provide you with a robust foundation. This session, you will gain not only just theoretical knowledge but also hands-on experience that you can immediately apply to the real-world data challenges. As we discussed in the introduction, data is being generated at an unpredictable rate across virtual every aspect of our lives and business. However, the sheer volume of this raw data can be incredibly overwhelming. Imagine trying to manually sift through millions of records to find a specific pattern or answer a complex question. It's simply not feasible. This is where the power of structured data management comes into play. The solution involves two key components. First, databases, which are specialized systems designed to store and organize this data in a structured, accessible manner. And second, SQL, the structured query language which acts as a primary tool to communicate with these databases, allowing us to ask precious questions, retrieve relevant information, and transfer raw data into actionable insights that drive informed decisions. To guide our learning journey today, we are structured this masterclass into 7 distinct modules, each building upon the last to ensure a comprehensive understanding. We will bring with the absolute SQL fundamentals covering basic commands and database concepts. Then we'll move on to data aggregation and grouping, learning how to summarize large data sets efficiently. Next, we'll explore joining tables, which is a crucial skill for combining related information from different parts of your database. As queries become more complex, subqueries and common table expression, which is the CTEs, will help us manage that complexity. We will then dive into window functions, which are often advanced analytical capabilities beyond simple aggregation. Following that, we have data manipulation and transformation, which will teach you how to modify and reshape your data. Finally, we'll touch upon advanced SQL techniques that are particularly valuable for data scientists and analysts. This structured approach will ensure a smooth and effective learning experience. Let's jump right into preparing our environment for hands-on practice. Welcome to our first module where we will lay the groundwork of your SQL journey. We'll start by understanding the fundamental building blocks of how data is stored, which is relational databases, and then introduce the very basics of SQL itself. Think of this as learning the alphabet and basic sentences before we write a novel. We'll cover what tables are, rows and columns are, and how SQL allows us to interact with them. This foundational knowledge is crucial because almost all modern data analysis, especially in business intelligence and data science, relies heavily on understanding and querying data stored in relational databases. Getting these core concepts right will make your entire learning process much smoother and more intuitive as we build up more complex topics. Before we dive into SQL, it's crucial to understand what kind of system SQL interacts with. The term you will hear most often is RDBMS, which stands for Relational Database Management System. At its core, an RDBMS is a software system used to create, manage, and retrieve data from relational databases. What makes a database relational is the way data is organized. Instead of storing all information in one giant unstructured block. Relational databases break data down into multiple discrete tables. Each table is a spreadsheet with rows and representing individual records, like a specific customer or a single product, and columns representing attributes of those records, like a customer name, email, or even product's price. The relational part comes from the ability to define relationship between these tables using common fields called keys, which we'll discuss soon. This structured approach ensures data integrity, reduces redundancy, and makes it incredibly efficient to query, manage large volumes of interconnected information. Think of it as a meticulously organized filing cabinet where related information is stored in separately well-indexed folders rather than a single chaotic file. So if RDBMS is the system that stores and manages our data, then SQL is the language we use to communicate with it. SQL stands for Structured Query Language. Let's break those words down. Structured refers to highly organized way data is stored in relational databases, in tables with rows and columns as we discussed. Query is the act of requesting information from databases, asking specific questions to retrieve the data you need. And language implies set of commands and syntax that both you and your database understand, allowing for precious interaction. Essentially, SQL is standard programming language for managing and querying data stored in an RDBMS. It's the bridge that allows data analysts, developers, and data scientists to interact with these vast repositories of information. Whether you want to retrieve specific customer detail, calculate total sales for a month, update a product price, or even define a new table structure, SQL provides commands to do it all. It's a universal language of data. These slides give you a high overview of different categories and types of commands available in SQL. You can see commands like select, update, insert into, and delete. These fall under data manipulation language, which are commands we will use to interact with the data itself within the tables, retrieving, adding, changing, or removing records. Then you will also notice commands like create database, alter table, drop table, create index, and drop index. These belongs to data definition language, which is DDL, which are commands we use to define, modify, and manage the structure of our databases, such as creating new tables, modifying existing ones, or defining relationships. Don't worry if these seems like a lot right now. We will be covering the most important of these in detail through the masterclass. Specifically, select will be our very next topic, and we'll dive into insert, update, delete, create table, alter table in module 6. This slide serves as a helpful visual roadmap of a powerful tool within the SQL language that we'll be exploring. The select statement is arguably the most frequently used command in SQL, as it's how we retrieve data from your database. It's our primary tool for asking the database, show me this information. You specify which column you want to see. If you want all the columns from the table, you can use asterisk. For example, we have select asterisk from customers would display every piece of information about every customer. However, it's often more efficient and practical to select only the specific column you need, like select name, last name, email from customers. The from clause is equally essential as it tells SQL exactly which table you desire data resides in. SQL wouldn't know where to look for columns you have requested. Mastering these two keywords is your big step in communicating with database. An example of both the commands is select asterisk product name, comma price from this product, which is selecting product name column from the product table. Once you know how to select data, the next crucial step is to refine your results to focus only on what's relevant. The where clause allows you to filter rows based on specific conditions, ensuring you only retrieve the data that meets your criteria. You can use various comparison operators like equals, greater than, or less than, and combine multiple conditions using logical operators like and or. For instance, you might want to see sales only for a specific product category and above a certain quantity. After filtering your dataset, you will often want to organize your results in a meaningful way. The order by clause lets you sort your data based on one or more columns, either in ascending order, which is often the default one, or even descending order. This is incredibly useful for quick identifying the highest or lowest values, for seeing data chronologically to observe trends, or simply for presenting your results in structured, readable format. Combining where and order by allows for a very precious data retrieval and presentation. An example of both clause being select asterisk from sales where quantity 5 order by sale data desk implements to select all sales where quantity is exactly 5. Finally, the limit clause is a simple yet incredibly powerful tool for managing the size of your results set, especially when dealing with very large databases. Retrieving all matching rows can be insufficient, time consuming, and often unnecessary, particularly if you are just looking for a quick overview of the top few entities. Limit allows you to return your query. For example, if you want to find the top 3 expensive products, you would combine select asterisk from products order by price decrease to ensure that they are sorted from the highest to the lowest, and then add limit 3. This command is particularly useful in scenarios like implementing pagination of web applications, or when you are performing exploratory data analysis and just want to sample a portion of your data to understand its structure and content without overwhelming your system on your screen. It's a fundamental tool for optimizing query performance and managing output. Before we start doing any practical part, there are two ways you can actually run SQL code. One is by downloading the SQL editors such as mysql, and the second way, which is an online SQL editor. For today, I'll be using Programmis, which is an online SQL editor. So as you can see, this is the window for it, and already they have a few of the data sets which you can practice in. So let me start creating a table, which is a basic, so that we can work upon it. So for creating, the code will be create table. Let's name the table customer, and you can give the values for it or the columns for it. So the columns will be customer ID, and you have to mention the data type too. So customer ID will be my integer data type, and this will also be a primary key in the table, which is going to be a character. And I'm going to limit the characters to 50. And similarly, we have last name, which is also going to be a character. And also I'm limiting this to 50. And let's have email ID too. Email ID is a varchar, which is a character. And let's limit that to 100 characters. And finally, let's have the registration date. And the type would be the date type, which is a series. And then let's close it. So when I run this, it should ideally create a table with customer ID, first name, last name, email, and the registration date as the columns, but it should not have any other table or any other inputs inside it. So when I run it, firstly it shows it's successfully run, and you can see here my table is here with customer ID, first name, last name, email ID, and registration date, and the table is empty. Now how do you fill in values for this? So the command is insert into. This programming language is not case sensitive, but most of the professionals use the keywords as caps and the names or the column names as a small case. So firstly, when you have to insert in any of the name or last name or feed in value, we have to use insert into. And what are the IDs that you're going to insert? I'm going to insert customer ID. Then I'm also going to enter first name, last name, email, and registration date. And what are we entering? We're entering values. So after this, you can just open the braces, and with the separation of quotes, you can enter the customer ID and then their first name with separation of comma. Let's say Alice, comma. And next we have to give his last name. So let's see, Smith. And then we have email ID. Let's say smith@gmail.com. So here I have missed this. So yeah. And then we have to give the registration date, which I'll give it like 23/01/15. This is one of our data that is going in. Let's see if I push only this much, what will be the answer. I ideally have to get this data set over here. So let's just run this. I just erased the previous create table and run this code which was not executed. So here you can see I have entered the value of 1, the first name being Alice, last name Smith, and an email ID being provided, and as well as a registration date. So I'll create 2 more tables with the values inside it. So I've created 3 tables. One is customer, and then we have products with product ID, product name, category, and price. And lastly, I have the sales column or a table, which is sales ID, customer ID, product ID, and sale data. I have some data. I've also added shipping also. But rather than that, we can play with the data sets. So the first query that will be executing is select statement. So it is supposed to select any column, specific column, or the entire table. So for that, we have select asterisk, and say let's select the column of customer, sorry. And let's run this. It should display the entire table. So here you can see all the entire table is being displayed. Now if I want a particular column, for that, here I should add a filter. Instead of asterisk, we have to add what are the things that what columns has to be displayed. So let me display only the first name and the last name. Last name. So let's execute this. It should give me only the first name and the last name column. So as you can see, we have only first name and last name. Similarly, any 2 rows. Then let me filter out using a greater than 100 rupees. Let me select a product name which is 100 and more than 100 rupees. So we have select product name, which is there in the products column, and then we have price. Let me display then from, not from the customers table, from products table. And then the condition is, the where clause is the price should be greater than 100 rupees. So let's run this. Okay, product, check for any errors. So it should give me the product name where the price is greater than 100. So you can see laptop pro cost 1200 and a desk chair ergonomical cost 250. These are the two products which have a price greater than 100. Now let's go to the next one, which is select the entire table, which is asterisk, and from sales, let's say I need the order by decrease. I want to arrange it in descending order. So we have order by, let's say price. I want to order the price from descending order. So for descending order, by default, it's going to be ascending order. So just give it DESC, which is a short form for descending order. And let's run the code. Search column price. Okay, so I think I've selected the wrong column. We have from sales, no, from products. So the column is in products. So now you can just run the code and you can see here the highest is 1200 and then it decreases as we go down. So for ascending, we can use ASC as the command. Now let's create a code which combines everything, that is selecting email of any two newest customers which we want to reach out the latest in the sign up. So we have to basically check which are the two new registrations and we have to add a decreasing order by. So for that we have select the column of email which we are majorly checking for, and also we need registration date. This is from which column? Sorry, which table? It is from customers, customer. And then let's order it by registration date. And let me put a descending filter and let me limit it to 2 as well. So let's see the answer. So here you go. This is the to registration which is recently registered. Welcome to module 2 where we unlock the power of summarizing data. While selecting individual roles is useful, real insight often comes from understanding patterns across many records. Data aggregations allows us to condense vast amounts of information into meaningful summaries like totals, averages, and counts. This is crucial for answering questions like what was our total revenue last quarters or even what's the average order value. Instead of looking at every single transaction, we can get a high-level overview that's essential for reporting and strategic decision making. We'll explore the various aggregate functions SQL provides and how to apply them effectively to transform raw data into digestible matrices. This module is all about moving from granular details into valuable summaries. SQL provides a set of powerful built-in aggregate functions that perform calculations on a set of rows and return single summary values. Let's look at the most common ones. Count is used to count the number of rows or null values in a specific column. For instance, count asterisk gives you the total number of records in a table, while count email would count only customers who provide an email address. Sum calculates the total sum of the values in a numeric column, perfect for adding up quantities sold, total revenue, or even total expenses. Average computes the arithmetic mean or average value of a numeric column, giving you a typical value. Minimum and maximum retrieve the smallest and the largest value respectively from a specific column, which can be useful for identifying outliers or ranges. These functions are your first line of defense against data overload, transferring raw detailed data into concise, digestible matrices that are easy to understand and report on. While aggregate functions gives you grand totals of entire table, the group by clause takes aggregation to the next level, allowing you to apply these functions to groups of rows that share a common value. Think of it as creating subtotals in a spreadsheet where you might sum sales for each product category individually. Instead of getting you total sales of all products across your entire data set, you can group using group by product ID to get total quantities sold for each individual product. This is incredibly powerful for segmenting your data and understanding performance across different categories, regions, customer segments, or even time periods. When you use group by, any column in your select statement that is not part of aggregate function must be included in your group by clause. Ensure that SQL knows how to group the non-aggregated columns to produce meaningful summaries for each distinct groups, providing a much more granular view of your aggregated data. You have learned that where clause filters individual rows before grouping or aggregation takes place. But what if you want to filter the groups themselves based on that results of aggregate function? That preciously what having clause is for. Having is used to filter the output of a group by clause. For example, if you calculate the total sales of a product category using sum and group by category, you might then want to see those categories where the sum of the sales exceed a certain threshold, say 1,000 rupees. You cannot use where because the aggregation hasn't happened yet at the where clause stage. Having allows you to apply conditions directly to aggregate results, giving you fine-grained control over which summarized groups are included in your final output. This distinction between where and having is a common point of confusion for beginners, but understanding is the key to write effective analytical queries. For example, this is statement which is select category average price from products group by categories having average price greater than 100. This SQL query retrieves the categories and their average product prices, but only for those categories where the average price of products exceeds 100 rupees. Let's see some practical examples of data aggregation and grouping. So firstly, for data aggregation, the first command that comes to mind is count. So let's use that. So let me use select and count. What we have to count from the entire table. So entire table is asterisk, and then from which table? From sales table. So this is going to count how many times we have made a sale. So the count is 20. Similarly, what if you have to do a sum? Sum of the quantity. Sum of the quantity. So it will be sum quantity ka table, quantity ka column, and we have put a condition as total items sold. And it is from which table? It is from sales ka table. So this should ideally give individual items which have been moved. So which is 25. This is the total items sold. So how do you name this column? Just add as and whatever name you want to give the table as. Next, we'll explore average. So for average, we have AVG. Now let me take the average of the price. Now price is from, let me give me a name as average product price. This is what I'm going to name it. And price is from which table? Price is from products table. So it will be product. And let's execute this. So this is the average price of each product. which is 202.2211 or so. Next, we'll explore minimum and maximum, which is the cheapest product and which is a highest product. So let's IN, this is for minimum. We are calculating in which column? Price. And this, let us name it as cheapest. And then for maximum, again from the column price, let's name it as expensive. And these both are from which column? It is from sales column. Close it and run it. So here there is no such column named price. So check with the, okay, so under products we have price. So let's rename the table name. It should be products. Now let's run the SQL code. And here you can see I have made a spelling error. So let's rectify it and run it. So we have cheapest being 20 rupees and expensive being 1200 rupees. Next, how do you use group by? So let us imagine we have to calculate a total quantity sold per unit product ID. So this tells us which products are moving the most. So for that, we need select product ID. We need the product ID to remember which product is selling the most. And then let's calculate the sum of the quantity, number of items, and name it as total. Total quantity. And then again, these both are from which table? Sales. And then I'm grouping them by product ID. Let us see if this will work. So here you go, product ID. So 101, the product ID is sold the most with 3 in number, and there are 8 in number also. So you can add a increment or a decrement function to see which product ranks number 1 and number 2. Now, how is having function used? So suppose you have to find a product category where average price is over 100 rupees. So how do you do that? Which category tends to have the higher period item? So for that, I'll write a query which is select category and the average price. Let me name this column as average category price. And then this is from which table? It is products. And I'm grouping them. Sorry. So I'm going to group by category. Also, I'm going to have a having function. So it is having average price. Which is greater than 100. Let's say decimal point and close it. Let's run the code. And here you can see the average price of electronics is 288 and furniture is 250. Welcome to Module 3, a critical turning point in your SQL journey. Joining tables, up until now, We have primarily focused on querying data from a single table. However, in the real world, data is rarely confined to one place. Databases are designed to be relational, meaning information is distributed across multiple, interconnected tables to avoid redundancy and maintain data integrity. For example, customer detail might not be one table, product information in another, and sales transaction in a third. To answer complex questions that require information from these different sources, like which customer bought which product or what are the most popular products among new customers, we need a way to combine these data. This is preciously what SQL joins allows us to do. Intelligently link related data across different tables to create a comprehensive, ununified view, enabling much richer and more insightful analysis. Before we dive into different types of join, it's essential to understand the concepts of keys in relational databases as they are very foundation of how tables are linked and how data integrity is maintained. A primary key is a column or a set of columns that uniquely identify each row in a table. Think of it as a unique ID number for every record. No two rows can have the same primary key and it cannot contain null values. For example, customer ID in the customers table is a primary key ensuring each customer's record is a distinct one. A foreign key, on the other hand, is a column in one table that refers to the primary key in another table. It establishes a link or relationship between the two tables. For instance, customer ID in our sales table is a foreign key because it refers back to the customer ID in the customers table. This relational design is incredibly powerful because it prevents data duplication, ensures consistent across related tables, and allows us to efficiently query interconnected data without storing the same information repeatedly, which saves space and reduces errors. Now let's explore most common frequent use types of SQL join. The inner join is the most fundamental and acts like an intersection. It returns only the rows where there are matching values in a specified join columns in both of the table being joined. If a record is in one table doesn't have a corresponding match in the other, it simply excludes from the result. Next, we have the left join. This join is designed to return all rows from the left table and only the matching rows from the right table. If there is no match in the right table for a row in the left table, the columns from the right table will simply show null. This is incredibly useful when you want to see everything from your primary table and enrich it with data from another. Even if the same records don't have a direct match, the right join is the symmetrical opposite of the left join. It returns all rows from the right table and only matching rows from the left table, with null values or non-matches on the left side. While less commonly used, that left join in practice, it serves specific purposes when you analytically focus on primary on the right table data. For example, the above SQL query would retrieve the sale ID, quantity sold, product name, and price of all sales by linking each sale record to its corresponding product record. Beyond the basic inner, left, and right joins, SQL offers more specified join types for complex scenarios. The full outer join, which is the most inclusive join, it returns all the rows from both left and right table, regardless of whether there is a match in the other table. If a row from the left table doesn't have a match in the right side columns will be null. Similarly, if a row from the right table doesn't have a match in the left side columns will be null. This is practically useful when you want to see all the data from both the sides and identify any mismatches or records that exist exclusively in one table but not the other. Note that the exact syntax of full order join can vary slightly between different database systems, and sometimes it's simulated using a union or left and right joins. Lastly, a self-join is a fascinating concept where you can join a table to itself. This might sound communicative, but it's incredibly powerful for analyzing hierarchical or self-referencing data within a single table. A classic example of the employee table where each employee has a manager ID that refers to another employee ID with the same table. By self-joining the employee table is itself, you can easily retrieve an employee's name alongside their manager's name from the same data set without needing to separate manager's table. This technique is invaluable for organizational chats, bill of material structures, or any data with a parent-child relationship with a single entity. For example, the above query retrieves pairs of employees and their corresponding managers from a single employee table. It does this by joining the table to itself, matching an employer's manager ID with another employee's employee ID to identify the manager. The output will show you two columns, one for the employee's name and one for the manager's name. So talking about inner join, let's execute inner join. We'll see what will be the output. So when do you use inner join? To get the product names from all the sales transaction. If you want to see what product was actually sold in the transaction or not, just the IDs. So for that we have select s dot sale ID and let's say p dot product name and also s dot quantity and s dot unit price. And this is from which table? We have sales and then s. And we want inner join, so let's mention that from products p on s dot product ID, which will be equal to p dot product ID. So this should give us an inner join. So yeah, so this will be your inner join. Similarly, you can perform a right join and a left join. But here I'll just show you how to create a self join to demonstrate a simple employees table. Okay, so for here I'll create a fresh table. Just create table and let the name be employee. And let's give the column name as employee. Table name is employee and the column names being employee ID and which type? Int, and I'll make it as primary key. And then we have, let's have employee name, which is in character format, and let me give the value as 10. And what else can we add? We can add manager ID, which is in int. So this is a table. So here you could have seen employee, here employee ID, and we have employee name, and also we'll have manager ID. This is created here. So I've added few values over here and also inner join by creating a temporary employees table, alongside their manager pulling both pieces of information from the same table, showcasing how to analyze hierarchical data. So let me just execute this. So let us run this code. And here you can see I've added few of the inner join items here in the columns. Welcome to Module 4, where we tackle the art of managing complexity in SQL queries using subqueries and common table expressions, or known as CTEs. As your data analysis questions become more sophisticated, a single select statement with a simple where and join clause might not be enough. You'll often find yourself needing to perform intermediate calculation, retrieving a specific set of data that then feeds into another part of your query, or break down a multiple step analytical process. This is where subqueries and CTEs become indispensable tools. They allow you to break down complex problems into small, more manageable, and often more readable pieces, making your SQL code more organized, easier to understand, and significantly simpler to debug. We'll explore how each of these powerful features help you write more efficient and maintainable SQL. A subquery, also known as inner query or nested query, is simple select statement embedded within another SQL query. Think of it as asking a smaller specific question first and then using answer to make smaller question to help resolve a larger one, more complex one. Subqueries are incredibly versatile and can be used in several parts of SQL statements. A very common use case is where clause. Where is the subquery can generate a list of values that are outer query and then uses for filtering, often with an operator like in or exist. For example, if you might want to all your customers who have purchased a specific product, which involves first finding the customer IDs from the sales table for the product and then using those IDs to retrieve customer details. You can also place subqueries in the select clause to return a single aggregated value for each row of the outer query, or even in the form clause, where the result of the subquery acts as a temporary virtual table, sometimes called derived table, that you can then query further. While powerful, deeply nested subqueries can sometimes become hard to read and debug, which leads us to our next concept of CTEs. Common Table Expression or CTEs are a modern and highly recommended feature in SQL, defined using the with clause. They allow you to create a temporary named results set that you can reference within a single select, insert, update, or delete statement. The primary benefit of CTE is significantly improvement in readability and maintainability of complex queries. Instead of nesting multiple subqueries, which can quickly become difficult to follow and debug, CTEs lets you break down your logic into distinct, named, sequential steps. Each CTE can build upon the previous one, making your thought process explicit in your code. For instance, you might define one CTE to calculate total sales per product and then another CTE to find average of those totals. And then you will find query selects from second CTE. While CTEs are temporary and only exist for a duration of the query in which they are defined, they are incredibly powerful for multiple step calculation, recursive queries, and simply making your SQL code cleaner, more understandable, and more modular for yourself and others who might read or maintain it. They promote a more organized and logical approach to writing advanced SQL. Welcome to Module 5, where we introduce one of the most powerful and versatile features in SQL for advanced analytical tasks. Windows function, while aggregate function like sum, average, collapse rows into single summary window, functions allows you to perform calculations across a set of related rows without collapsing them. This means you get to aggregate value alongside each individual row, providing crucial context that simply group by statements cannot. For example, amount of their running total of sales in all the same result set. The capability of invaluable for tasks like ranking items with a category, calculating running totals over time, or comparing a row's value to a previous or next row, which are common requirements for financial analysis, trend identification, and performance monitoring. Understanding window function will significantly elevate your data analysis capabilities and allow you to answer more complex business questions. The core syntax of any window function involves a function name followed by over clause. The over clause is where you define the window or set of rows over which the function will operate. This is magic behind window function as it tells SQL which row are considered related for the current calculation. Within over, you can use two option but powerful subclauses, which is partition by and order by. Partition by divides your data into separate independent groups, similar to how group by works, but crucially, it doesn't. So with collapsing the rows, the window function then performs its calculation independently with each of these partitions. For example, if you're calculating a running total of sales, you might partition by customer ID to get a separate running total for each customer rather than one grand total. Order by within over clauses specifies the logical order of rows within each partition. This is absolutely crucial for function that depends on sequence of data such as ranking function or calculating cumulative sums, ensuring the calculation is performed in the correct order. Within order by, the results of some window function might not be deterministic. Ranking function is one of the most common and intuitive application of window function, allowing you to assign a rank to each row within specified partition based on given ordering criterion. There are three primary ranking functions, each handling ties slightly different. Row number assigns a unique sequential integer of each row within its partition starting from 1. If there are ties in ordering criteria, the row number assignment along the tied rows are attributary but unique. Rank assigns a rank to each row, but if there are ties, all tied rows receive the same rank. And next rank skips numbers. For example, if two items are tied for the first place, they both get ranked 1 and the next item gets ranked dense rank. Is similar to rank. It assigns consequently ranks without any gaps even in the presence of ties. So if two items are tied for the first place, they both get rank number 1 and for the next item gets rank 2. Choosing the right ranking function depends on how you want to handle ties, whether you need to consciously sequence the ranks for your analysis, such as finding the top end performers or identifying the order of the events. Beyond ranking, window functions are incredibly powerful for various analytical calculations that involve looking at preceding or succeeding rows. Lag and lead are value functions that allows you to access data from preceding or succeeding row within you to identify window respectively. Lag, which retrieves the value from the column from a row of offset rows before the current row, and default value is used if no such row exists. Lead does the opposite, fetching from a row offset after the current row. These are invaluable for time series analysis such as comparing current sales to yesterday's sales or analyzing sequential events like a customer's current purchase compared to their last ones. Furthermore, window functions are perfectly suited for calculating running totals and moving averages. A running total achieved with sum over order by cumulative sums values as you progress through the ordered data, showing the accumulation of a metric over time. A moving average, typically calculated with average over, smooths out daily over period to period fluctuations by averaging values over a specified window of rows, which helps to identify underlying trends more clearly by reducing noise. These analytical capabilities are fundamentals in financial analysis, sales forecasting, and many other data-driven fields where understanding trends and comparison over time is crucial. Welcome to Module 6, where we shift our focus from merely retrieving and analyzing data to actively changing and structuring it. This module covers data manipulation language, which is DML, and data definition language, which is DML, allows you to add new records, modify existing ones, and delete unwanted data, which are fundamental operations in any database system, essential for keeping your data current and accurate. DDL, on the other hand, gives you the power to define and alter the very structure of your database tables, such as creating new tables from scratch or adding new columns to existing ones as your data requirements evolve. We'll also touch upon data type conversion, a common task when data needs to be presented or used in a different format for calculation or integration. These skills are crucial for maintaining the accuracy and relevance of your database, as well as preparing data for specific analytical needs or ensuring compatibility with other systems. Data manipulation language or DML consists of commands that allows you to interact directly with the data stored within your tables. The insert into statement is used to add new rows or records into a table. This is how new customer signups, new product entities, or new sales transactions are recorded in your database. You specify the table name and the values for the columns, ensuring the data types match. The update statement is used for modifying existing data in one or more rows. This is incredibly powerful for collecting errors, reflecting changes in status, or updating information like a customer's email address or product's price. However, it comes with a critical warning. You must always use where clause with update to specify exactly which row you want to change. Without it, you could inadequately modify every single record in your table, leading to massive data corruption. Similarly, the delete statement is used to remove rows from a table. Just like update, it's absolutely vital to use a where clause to target specific rows for permanent deletion. Without it, you could wipe out your entire table's data. In many professional environments, soft deleting, which is marking a record as an inactive with a status flag rather than permanently removing it, is often preferred for auditing and data recovery processes, offering a safer alternative to a full delete. Beyond manipulation, the data itself, SQL provides data definition language, which is DDL, commands that allow you to define, modify, and manage the structure of databases. The create table statement is how you initially define a new table, specifying its name and the names of its column and data type for each column. Data types are crucial because they dictate what kind of information a column can hold, how much storage it requires, and how it behaves in queries. The alter table statement is used to modify the structure of an existing table after it has been created. This can include adding new columns, dropping existing ones, or changing the data type of a column. This flexibility is essential as your data requirements evolve over time. For instance, you might decide to add a phone number column to your customer table. Finally, we have the cast function. While technically a function rather than a DDL command is often used to conjunction with data transformation, it allows you to explicitly convert a value from one data type to another. For example, converting a string that represents a number into an actual numeric type so you can perform mathematical operations on it, or formatting the data into specific string representing for reporting or display purposes. Understanding DDL and data types is fundamental for designing and maintaining robust database schemas. Welcome to our final module, Module 7, where we will delve into some more advanced SQL techniques that are particularly valuable for data scientists, analysts, and anyone working with complex data sets. While the previous modules covered the core functionalities, these advanced tools allow more sophisticated data cleaning pattern, matching, and abstraction, enabling you to extract deeper insights and streamline your analytical workflows. We'll explore powerful functions for working with different data types like dates and strings, touch upon regular expression for flexible patterns matching, and introduce concepts like views and stored procedure with the help of creating reusable and efficient database objects. Mastering these techniques will truly elevate your SQL proficiency and open doors to more intricate data challenges, preparing you for the real-world data science problems. In the real-world data, you will constantly encounter various data types, and SQL provides a rich set of functions to manipulate them effectively, which is crucial for data cleaning and preparation. For dates and times, you can extract specific components like the year, month, or the day using the functions that vary slightly by database systems such as strft time and SQLite year, month, or mysql extract in PostgreSQL. This is crucial for time series analysis, identifying seasonal trends, or grouping data by specific time periods for reporting. You can also calculate difference between dates, for example, to determine how long a customer has been registered or the duration between two events. For strings, SQL offers between powerful manipulation function, which is upper and lower converted text to uppercase or lowercase, useful for standardizing text data to ensure consistent comparison. Strings allows you to extract a portion of a string, which is handy for passing codes or identifiers, while length returns its length concat, combines multiple text columns into a single string, such as creating a full name from a separate first and the last name columns for display. These functions are indispensable for data cleaning, formatting, and preparing text data for analysis. To wrap up our advanced techniques, let's briefly discuss these powerful concepts that enhance your SQL capabilities. First, regular expression, often abbreviated as regex, offer an extreme flexible and powerful way to search for or manipulate complex patterns within the text data. While basic like can handle simple wildcard, regex allows you to define intricate patterns such as validating email formats, extracting specific codes or number from long unstructured text fields, or finding words that match a specific structure. The exact function or operator varies by database system. Second, views are virtual tables created from the result set of a SQL query. They don't store data themselves but rather provide a simplified, predefined window into your data. You can query a view just like a regular table, which can excellent from simplifying complex join or aggregates that you can use frequently for a less providing a controlled abstraction layer of users who only need to see a specific subsets of data without understanding and underlying complex queries. Finally, we have stored procedures, which are pre-compiled collections of SQL statements that are stored in the database server. They encapsulate complex business logic, can accept parameters, and offer significant benefit like improved performance, enhanced reusability, and improved security. While their syntax is highly database specific, understanding their purpose is key for advanced database interactions, automating and building robust data solutions. The skills you have gained today is not merely technical. They are foundation for critical thinking and problem solving in the domain that relies on data. SQL isn't just a language for databases, it's a superpower for anyone who wants to make sense of information, drive impact. With SQL, you now have the ability to precisely extract specific information, no matter how deeply buried it is. Your datasets allowing you to answer very targeted questions. You can identify crucial trends and patterns that are often hidden in raw, unstructured data, enabling you to uncover valuable insights into performance, behavior, and anomalies. You can summarize vast amount of data into concise, actionable reports and dashboards, transferring overwhelming number into clear native that stakeholders can understand. Ultimately, mastering SQL empowers you to make truly data-driven decisions, impacting everything from business strategy and operational efficiency to significant discovery and public policy. This proficiency will serve you as a cornerstone of your analytical career, opening doors to countless opportunities. And that brings us to the very end of our SQL Fundamentals for Data Analysis course. I sincerely hope you found this session valuable and now you're feeling much more confident and excited about diving deeper into the world of data with SQL. Remember, the journey to becoming a data wizard is all about consistent practice and nurturing that curiosity to uncover insights. Thank you for watching and keep learning with Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.